So let's give me the overview is like that. I want to introduce a motivation of why do we want to make stochastic modeling. So this is it's actually my major aim. If I don't really manage to come to the technical part, it's not important. I really want to convey the message, why do we want to make stochastic modeling in fluids? So what is the aim? So we had another talk in the other auditorium, so it was already a motivation, but let me repeat this one, because we have this parallel session. So then I go to what kind of stochastic rotating shallow water equations we are using here. I'm going to talk about variational integrators, how we discretize these equations, and then also I present some numerical results. Let me start with the motivation. So why do we want to make uncertainty modeling, and why do we want to do stochastic modeling? Why aren't we happy with deterministic modeling? We can account for errors. So we have a lot of errors. We have errors in the model description, so we use shallow water equation for modeling. We have assumptions, there are stuff that is not resolved, we have numerical errors. All these kind of things contribute to an error in the forecast, in predictions of our model solutions. So we want to have an understanding of how large these errors are. So this is why we do uncertainty modeling. And then when we do this, how do we do this? So we have now a stochastic model that takes into account the errors by stochastic random processes, and then to somehow have an idea of the uncertainty, we run a couple of simulations. So this is illustrated here. So we start our model, our stochastic model, 20-30 times. It's called an ensemble run, and this, because of the errors, because of the randomness that we have, these models will differ. For instance, here, if we look, for instance, at this flow field here, and we look at the quantity, the potential vorticity here, Q, this will somehow diverge. There will be a difference in the different realizations. And from the spread of how this model realizations, each of these runs differ, we can infer what kind of error our model has. So we can now imagine, okay, is this good representation? This is now actually the task. If this spread is too large, we somehow don't really capture the error, the unknown stuff, and if it's too tiny, we don't really represent the error well. So we want to model, of course, by a good stochastic way, by a good stochastic model, the right amount of spread, and then we have a measure of how uncertain our model predictions are. So this is particularly important when we have weather forecast, climate models. We somehow want to have, with a 10-day forecast, we want to know, okay, how certain do certain events occur. So this is what we want. And the next ingredient that I'm always promoting is we want to have structure preserving discretizations. The easiest thing to think about is we want to have that our discrete model preserves, for instance, the mass. If we have a 100-year forecast and our model doesn't preserve mass, for instance, the oceans would just dry out during 100 years of implementation, of integration. So this kind of things are essential. But there are also other things that are not so obvious. So we want, at first we start with a consistent model that conserves this kind of things, energy and mass. And then we want to find structure preserving discretizations that preserve these key structure properties. So for instance, one important structure is this the RAM complex, the cohomology. So these differential operators, they form this complex, and for instance in finite element modeling, if you don't do this, you can show that when you have now a finite element model, it can converge but to the wrong solution. So if you don't fulfill this. So structure preserving gives you also a security that you converge to a right solution. So this is important. And other things that I'm interested here is our discrete version, our discrete equation should preserve a variational structure, a Hamiltonian structure. So I don't go too much into detail now here. I just wanted to point out why it is important. I already said, when we preserve this structure, we are sure that we have the correct solutions when we converge to solution. And also that the transfer between energies of different scales, here you see we have small scale, we have large scale, of this large-scale flow here. This is an instability on the northern hemisphere of the globe. Here, that energy are transferred nicely. We need to have, for instance, Hamiltonian structure preserved so that the energy transfer are correct. And also, we want to have statistical means correctly represented, and for this we need also certain structures to be preserved. So one structure of interest for us here, because we're working on a variational integrator, is we want to preserve energy as good as possible. Okay, so let's come to the stochastic equations. So what kind of stochastic equations we have. And first, I'm using here the rotating Shell-Watt equation as a test model. What these are and why do we use them? So the rotating Shell-Watt equation are of geophysical fluid models are our working horse. They are two-dimensional equations that share many important properties of a full 3D flow, but they are much easier to solve. So for this, we can prototype discretizations, things that we are interested in. So this is a very good way, a starting point of developing discretizations. So how do they look like? So we have two equations. Here we have the momentum equation. So we have two prognostic variables here, the velocity, that is the velocity of this water column here, which is governed by an advection term here in a vector invariant form. And here we have the the gradient, the potential, the gradient part, and nu, you can imagine nu is simply h, because when we say the bottom topography is 0, then nu is h. So just make it easier. And here we have the kinetic energy term. And then here we have the divergence term, which takes care that changes in the divergence of this flux also contribute to changes in the height. So this is our system, and we have F, so we have a rotating sphere, also a rotating plane. So, and these are models where we can model in an easier way three-dimensional flow on the sphere. Now we want to go to stochastic models, and here our answer is the following. So we assume that our large scale or our flow consists of two parts. It consists of a large scale slow component, which we can resolve with our computational model, and we model the unknown, the small scale, the fast stuff that is in the subgrid scale and which is not known, we model by a stochastic process. So the stochastic process, this sigma here, we have to determine somehow by initial data or by the flow field itself, but then we can somehow model what's going on the subgrid scale. But the large scale flow is resolved. So we have these ansatz now, and now we put it into a complicated but a consistent method of deriving stochastic equations. And here in a very easy case, as we've shown here in this paper, we can derive from a stochastic Reynolds transport theorem, we can derive stochastic rotating Shell-Watt equations, these are SDEs, that look in the following way. They consist of the deterministic part here. They are exactly like this one, a little bit differently written, you will see in a second why. But they have this deterministic term here, and they have the stochastic terms here. And let me explain a little bit. We have here now an advection term. And now when you see, this is the deterministic term here. So, and we see that here we have the stochastic term, and this stochastic term has the shape of an advection term. So when you put these two things together, you have u plus sigma dpt. So now by this ansatz, we have now a connection between the small scale noise and the large scale flow. So this is now a model that allows you to model that can represent the influence of small scale on the large scale flow. We will see this in the numerical section. So this is a very important part, that this shape of this form actually has now a meaning of how small scale can influence on the large scale. This is why the stochastic model is special, and it seems to work very well. And the other important part is that these are energy conserving equations. That means, so when we put here in energy through this noise term, this is dissipated away by this kind of Laplacian, right? So if A would be a constant, this is simply the Laplacian. Right? It's a little bit more complicated if A is a covariance matrix, but it doesn't matter here. For an understanding is each of these if you run one realization now, this is an energy conserving realization, and the energy brought in by the stochasticity is dissipated away. So our aim, as I said in the beginning, we want to have stochastic structure preserving things that preserve mass, that preserve energy. So this is already, so that means now we have a stochastic continuous model that we can represent like that. So now on the continuous model we have a consistent model. This is also something new. Before, usually the people just put noise on the right hand side term as forcing. These models needed intrinsically already some kind of diffusion, otherwise they've blown up. So this is now a consistent formulation. Now the discretization was now, and here we come to the why I'm here also at this conference. So the deterministic part here, we use a variational integrator that I developed together with François, where we somehow have for the rotating Shell-Watt equations, this deterministic core is done by a variational integrator. So this preserves energy well, and then our idea was, because it's very difficult to discretize them structure preservingly, so we simply used here standard finite difference operators to discretize the stochastic terms, and we just had a look how it performs. How important is the influence of this one to this one? Yeah, let's go on and let's see how it works. So and now the representation of the stochastic terms. So it's important now to somehow model this, the noise. How do we model this? How do we somehow model this small scale stuff? So, for instance, these terms here can be represented by this sum over eigenmodes, over spatial modes, where we see, okay, this stochastic process here can be represented by a standard Gaussian variable and some kind of spatial modes and some kind of eigenvalues. So we can, for instance, now take the initial condition, make an EOF, make a singular value decomposition. We have a bunch of eigenvalues and we have eigenvectors, and then we just take those things when we go from 0 to NT, we just take the last parts that are responsible for the high frequencies, because this is what we cannot resolve. This is what we want to model. The first part of the spectrum we discard because we don't need it. This is what we resolve, and the high resolution part we do like that. So we have now a way of representing by the initial conditions or by the flow field itself. We have a way of modeling, of really somehow finding from the flow field how this small scale structure could look like. And this is what we do. We have two versions of building the noise. We have an offline version where we build EOFs from high resolution initial conditions. We calculate this spatial modes, and we calculate the eigenvalues, and then we can calculate these noise terms and the corresponding covariance matrix. And we have also an online version that does this in runtime from a coarse resolution sample. Okay, the variational integrator, so I'm running out of time, I already see, okay, so I have to be a little bit faster, but this is easy. For the community here, it's not a complete, okay. I just have to speed up, sorry. I just give the essential elements that we need. So our vector field is in fact represented by a discrete Lie algebra, where the matrix element, so these are matrices, this Lie algebra is represented by matrices of matrix elements of matrix A, and the elements of these matrices can be somehow represented, by that, which means actually they are fluxes over each of the cell. So they are proportional to fluxes over these cells. So when we talk about A is now a Lie algebra representation of the fluid velocity, let's say like that. This is what you have to understand. And the D's are averages of a function of the height field. So the height field is then an average of, we have a function, and the average of this function over this height field is then associated to the fluid density D. So we have these two ingredients. We have the velocity, you can call it A, and we have D, it's the height field. And now to have our discretization, we write now our discrete Lagrangian, and now we do simply variations, but now on a discrete level. We have our Lagrangian, we write it exactly the same way as the continuous one. We have the kinetic energy term, we have here the potential energy term and the rotation term. we define a discrete pairing, because to do functional derivatives we have to define a pairing, otherwise we don't know how to do variations. And we can calculate discrete functional derivatives, they look like that. And now we derived a Euler-Poincaré equation that gives us the momentum equation and the continuity equation. So this is now the discretized Euler-Poincaré version of our momentum equation. And we can now put in here these functional derivatives and we come to the discrete scheme. I show in 2 slides how this looks like. It's also not so important. What's important is that this gives us now a structure-preserving discretization of our shallow water equations. And next, this one, and next we can add a Casimir dissipation. What is this? This is the Casimirs of the system. They are not controlled, they might be very noisy, and by this we have a scale selective dissipation of some Casimirs that we put here in. This is an additional term. The first term stays the same, and we have an additional term that now takes care of the Casimir. In our case, it's the potential entropy that we have to control. Otherwise, at some point, our simulation might blow up. So this is what's happening here. So I don't go into detail. It's just that our system, we could extend the former system that we derived somehow 2019 in the 2021 paper to this Casimir dissipation. This is now our deterministic part now that has control over the Casimir. And just for comparison, usually what's done in stochastic models, you use a biharmonic Laplacian to dissipate stuff away. This is just for comparison. And now, as promised, the full system. I don't expect you to read this, it's just for completeness, and everything can be written explicitly. We have a deterministic system with stochastic terms, and we now check with respect to either we use our Casimir dissipation or we use standard Laplacian dissipation. We come to the numerical results. Now when we look at the deterministic model, this is what I said. When we don't have dissipation in our model, we run here for 100 days. So we have a flow field on the atmosphere, we look at the northern hemisphere, and these things really accumulate a lot of noise. This is the entropy that accumulates here up. Energy is conserved because we have this variational integrator for a very long time. So, but you see, this is very noisy. So then, in this paper with Rüdiger, with Brecht, and François, so we derive this Casimir dissipation. Now you see the vector field is the field is much smoother. You see also the energy is good preserved here. So it's now red. It accumulates a little bit, but it's very much controlled. But now you see that the entropy is dissipated away, and this is what we want. I can explain later on why, but this is what we want. And it's very well, it's in agreement with the reference. And if you don't do it, we can also use biharmonic Laplacian, but then you see also energy is dissipated away. When we go to the stochasticity, I speed up. So now, what's the important part is here now the following. When you have a deterministic low resolution run, in comparison to our stochastic low resolution run. These are low resolution run, and this is the reference. So you see that our stochastic model, by representing the small scale noise, can now much better represent this large scale flow, whereas a deterministic comparable model just fails. And this is because small scale features are represented by the stochastic processes, whereas the deterministic model, I have to be fast here, the deterministic model is here, it doesn't have small scale, the stochastic model does have. And now let me go on to the stuff that I wanted to say finally, and then when we compare now a standard biharmonic Laplacian versus our new Casimir dissipation stuff, we see that we can now, the red one is the Casimir dissipation. We can conserve energy. We have a scale selective dissipation of entropy, so this noise we can scale select dissipate. And this actually, you see that we have, with the scale selective Casimir dissipation, we are even closer to the reference because we don't drag out energy of the system. So we are even better now. And when you look at the spread, so the spread from the b-harmonic Laplacian was much thinner. So I said in the beginning that it's important that this is well represented. Whereas, so this is the reference here, the black one. This is the truth that we want to model. So the red one somehow covers this well, the new one, and the old one is not so good. Okay, with this I skip this one, and I come to the conclusion. So we derived this stochastic rotating Shell-Watt equation. What is important is that the new Casimir dissipation just doesn't drag out energy of the system, so it is more dynamic and it's closer to what we want to the reference. Yes, and this is the outlook. Thanks. Sorry.
Thank you very much. So maybe one question.
Very nice talk, thank you very much. Your velocity living in Lie algebra, however vorticities living in dual Lie algebra. And my question is, does your variational integrator preserve vorticity Kelvin's theorem, which can be also be preserved on discretized level?
Yeah. What do you know?
Yeah.
Does the vorticity?
Vorticity is lives in the dual Lie algebra. Yes. Yeah. So actually, this can be also conserved in variational integrator. It's a Kelvin theorem, basically.
Yeah, I know it from the numerical point. From the numerical simulations, this is preserved. I think when we go through the derivation, it's not. Is it as a constraint? The Kelvin theorem holds. Yes, this I know. So it should be. I think from the numeric, I do see that it is preserved in machine precision. So
thank you. Just one small. So your point is to preserve energy, but you also have dissipative member in your variational formulation, right? Mm-hmm. So how do you preserve energy because you have dissipation included?
You mean where
normally, if one use this energy preservation scheme, yes, then energy should be preserved in a certain level, right? Yes. But you have dissipative term, Casimir one, also in formulation. So that is not in collision one with another.
No, the Casimir one doesn't interact with the energy conservation. So the Casimir one, the B Laplacian, yes, does. The B Laplacian does, of course, take out energy.
Does your deterministic model preserve energy or not? Deterministic one?
Yes. In a symplectic way, in a variational way. It swings around 10 to the minus 8, 9. It's not too much. It's like a symplectic integral.
Okay, thank you very much. Let's thank Werner again.